Welcome back to ECE 441A, 541A. Homework number 2 is due today. Hopefully that doesn't surprise anyone. Exam number 1, which is more of a surprise if this surprises you, is scheduled for Friday morning. And if you're completely taken aback by that, I'm not sure where you have been. I think I've been announcing it consistently for a while. And the practice material for exam number 1 is on D2L. Lab number 1, I think, is going smoothly, I hope. It's not, the write-up is not due until after the exam, but the material that's covered in lab number 1 will be a part of exam number 1. So make sure that you can do system identification of an underdamped second-order system, which is what we will be talking about today, but you also have additional material from lab number 1 notes and video. Today what I want to do is talk briefly about the process for exam number 1. You've probably already know what that is if you've been looking at some of the previous exams. We'll discuss second-order system parameters. Essentially, what are these different coefficients in a transfer function and how do they map into regions or locations in the complex S-plane, and understanding that. And then we will present, I will simply provide you with this connection of time domain response data and how that translates into these coefficients of your transfer function. I'm doing that because I'm not sure how far I will go or get to in the derivation of those. We'll try to derive some of those, but if we do not get all the way through in the video, I will probably try to continue that with some AC notes, some after-class notes at the end of today's video. Here's the process for exam number 1. You will be allowed a sheet of notes. That's 1 for this exam, and you might want to keep track of that. For the second exam, you will get 2 sheets of notes, meaning don't trash that crib sheet or that note sheet unless you think it really failed you. Then maybe you can create a second one for the second exam, but you have front and back of 1 sheet. You can also print out a copy of table 2.3. That's the Laplace transform pair table in the textbook, and that particular page is actually on the website if you need that specific table. I really would prefer everybody having the same table and we all are referring to the same pairs when we talk about Laplace transforms. You can bring a calculator. Any calculator is allowed, an 83, an 84, an 89, an Inspire, an HP. Just don't bring a computer. You can't have a computer sitting on your desk. Something to write with, and in terms of writing, it's fine to bring a pen. Just cross out what you don't want me to look at. You may actually think after you've crossed it out, you might say, whoops, that was correct. Go ahead and grade that. Instead of spending time erasing and then having to rewrite, if you've written something down, probably just cross it out and say, don't look at this, and then if later it turns out you want me to look at that, you can go back and put an arrow or some kind of marking on that to let me know that indeed that was what you wanted me to look at. It's closed book, closed notes. That's class notes, no phone and no computer. And there are example exams on the website, and you shouldn't be too surprised by the format of Friday's exam or the exam that's happening the next time we meet. Are there questions about exam number 1? That means maybe you already have seen it, and if you could hand me a copy of that, then I could photocopy it. Never mind. It'd be nice to have the exam, I guess is what I'm saying, but hopefully it will be available on Friday. morning at 9. Here's what we want to do today. We want to now be able to identify or find, by doing some analysis, these coefficients, the B coefficient, the K, the M, and the gamma experimentally. Maybe we can't measure them physically. We do have the ability to measure the mass in our system, and we know that the carriage is also how big in terms of mass. That's a half a kilogram, and you need to account for that in your nominal mass. But maybe we don't have a way to measure the spring, although you might be able to put some apples on it and compress it a certain distance, and then you can get your spring constant of 400 newtons per meter or something, depending on how stiff that spring is, and your B. That's the damping due to, or it's now the coefficient that gives you the damping, and the damping is now proportional to the velocity of that moving mass M. This is the note card you have under your pillow that describes the dynamics of your system. You probably don't even need that note card now. Maybe it's been consumed by your dog. Unlike your homework, hopefully your homework was not eaten by your dog. That's due today. Here's the Laplace transform of that. It's second order. There's the s squared. And here is now the transfer function between the input u and the output x. And we simply take the output ratio, take the ratio of the output over the input, and find or write down our transfer function g of s. The last expression for that transfer function on the lower right hand of the screen is now written with a monic, M-O-N-I-C, denominator, or the leading coefficient has been normalized to 1. And a lot of times that's the way we will write a transfer function, so that we don't have to worry about that impacting our coefficients if we're now solving for some particular coefficient in the problem. We've now at least normalized the denominator polynomial. So I may sometimes just say, assume a monic polynomial in the denominator, or our denominator polynomial is monic. That's what I mean by it. We've now factored out the coefficient that's scaling the highest coefficient in the denominator. That g of s in black is parameterized based on the physical system. The mass, the spring, the dashpot, the gain coefficient gamma. But typically, we may just say, oh, this response looks second order. And we may just say, oh, then I know its structure. I know the structure of this second order system, independent of what makes those coefficients what they are. We can now say, oh, I have a numerator, and I may say this is a pure two-pole system, meaning I do not have any zeros in the numerator. If I say a pure two-pole system, I'm meaning I only have two poles in my transfer function. I obviously have some non-zero coefficient upstairs in the numerator, but there are no s's floating around, finite values of s in the numerator. And if you compare these two parameterized versions, these standard forms of the transfer function, you can start to relate the sigma, and hopefully when you see me write the denominator as this quantity s plus sigma quantity squared plus omega sub d squared, you immediately see where those poles are in the complex s-plane. They're to the left of the imaginary axis, a distance of minus sigma in real horizontal space, and then in the vertical direction, or in the imaginary component, they are a distance omega sub d away from the real axis. And I have two, and they're complex conjugate pole pairs because I have real coefficients in the denominator, polynomial. But sometimes we might like to write that in terms of natural frequency, omega sub n, and the damping ratio, zeta. That's what that curly symbol is supposed to be. That's now zeta, which is referred to as the damping ratio. So now we have this other second way of writing it, and you may see it written either way or both ways depending on how it's going to be used. But the main thing that we want to be able to do is, if we look at the far right hand side, we want to be able to figure out what is that constant coefficient in the denominator, which is really omega sub n squared in this parameterization. What's the linear coefficient, 2 zeta omega sub n, what's its value, and what's alpha? Can we find those by looking at a second order response of a pure two-pole system? That's what we want to do today. That's what you want to do in the lab. And now what I'm trying to do is show you how all of those different parameters can be related. So I think the way to look at this is to first not pay attention to what's in the highlighted space and just focus on the S-plane. So the S-plane has one pole, and I'm just showing one quadrant, the second quadrant. That pole is an X, and it's at minus sigma plus j omega sub d. The real component is minus sigma. It's in the left half plane. It has a stable response. The imaginary component is omega sub d. But now we can use our Pythagorean theorem and our trigonometry to interrelate all of these different variables, sigma and omega sub d. I give you a sigma and omega sub d, you can put down the x. Is that clear? I give you a minus sigma plus j omega sub d, you can plot down that x in the S-plane. Now, from that, you can find that theta. That's why I said you might bring a protractor. You can find the distance. The distance that pole is away from the origin, that's its natural frequency. That's omega sub n. And we can find that from Pythagoras. The Pythagorean theorem says sigma squared plus omega sub d squared is the hypotenuse squared, and the hypotenuse is omega sub n. And that's what's in the yellow highlight. I'm simply showing the connection between sigma, omega sub d. So sigma I might call the damping, omega sub d I might call the damped frequency of oscillation, and omega sub n, as we go through this semester, omega sub n, sometimes we'll actually draw a circle with that as a radius, and we'll say, where are our poles if they are omega sub n away from the origin? That's going to depend on the angle, theta. But in the yellow highlight, I've now tried to be color consistent with omega sub n being the hypotenuse and omega sub d being the damping, the damped frequency of oscillation. A squared plus b squared equals c squared gives us the first line. We solve for b squared. Then we have this sigma. If we kind of play with both highlights, we can find out what sigma is in terms of the hypotenuse and zeta. So the blue highlights tell us our trigonometry. That's our trigonometry review. The cosine of that angle theta is adjacent over hypotenuse, sigma over omega sub n. But we know that sigma is zeta omega sub n. And that now allows us to say that cosine of theta is actually that damping ratio zeta. So you give me that pole at minus sigma plus j omega sub d, I can compute theta. I can then compute zeta, the damping ratio. It's the cosine of that angle. Once I have zeta, Or once I have sigma omega sub d, I can find zeta and omega sub n. Now I have that entire denominator. I have that expressed in terms of zeta and omega sub n. I already had it in terms of sigma and omega sub d, depending on how you write it. You can also find an expression for sine of theta. That's opposite over hypotenuse, which is now omega sub d over omega sub n. And omega sub n times the square root of 1 minus zeta squared is omega sub d. And that shows us then that sine of theta, I might, in subsequent discussions, say, oh, that's the square root of 1 minus zeta squared. That's now beta. All of this will be available to you in the notes, but now we kind of, I hope, have a connection with me giving you a parameter or parameters or a pole pair. You can start to figure out what's zeta, what's omega sub n, etc. from that information. So what we want to do is use that analysis or that way of parameterizing our transfer function and be able to extract or connect it to a time response waveform. So let's now look at the step response of a pure two-pole system where the input is a constant of magnitude A. Its Laplace transform is then A over S, and we can now multiply G of S times R of S. And G of S is just alpha over the two complex conjugate poles times A over S. And we will be playing now with this particular structure and seeing how we can use this parameterized form of the step response, capital Y of S, and connect it to the time domain expression so that we can now make this connection between time domain data, experimentally measured points on the step response, and these parameters, sigma, omega sub d, and alpha. Or, written in terms of zeta and omega sub n, we could write the denominator in terms of those two parameters. You give me omega sub n and zeta, that's the same as me giving you sigma and omega sub d. And we want to now try to connect those with this time domain step response. This is an underdamped second order response, and I've now identified really two locations on that plot. Its final value, where did we eventually get to, and I'm labeling that as y sub fv, and where did we first peak? What's the value of that, and when did that happen? So we'll call that t sub p our peak time, and the value, we'll either call that y max or y peak. That's the first time that we peak after time t equals 0. If you've now identified that peak value and the final value, you can tell me what the percent overshoot is for that particular second order system. That's just its peak value minus its final value. That's the fractional difference between the peak and the final value divided by the final value times 100%. So if you have a 50% overshoot, and let's say y final value was 1, then y peak would have been 1.5. If you have a 100% overshoot, then y peak would be 2. Typically, well, it depends, but you may or may not want to tolerate a certain amount of percent overshoot. Maybe you can say, oh, I will accommodate a 5% overshoot, or I can absorb a 10% overshoot, but don't go to 50% overshoot. That's too much. But maybe in another case you might say, okay, I want 50%, but, or I can tolerate 50% because that will get me to my peak quicker. So there's always trade-offs in control. And Y final value, I've simply connected that to our parameterized expression. Hopefully you can see that here. If you applied the final value theorem and multiplied that by S and let S go to 0, you can hopefully see where these final values, these expressions for the final value, are coming from. One in terms of omega sub n, the natural frequency. And when I say natural frequency, what do you now see or think? The distance that pole pair is from the origin. That's your natural frequency. How far away from the origin is that pole? If I say sigma and omega sub d, that tells you sort of the rectangular way to get to that same pole. You walk over sigma and up omega sub d. However I give you that information, if I give you sigma and omega sub d, you should be visualizing in your head or on a piece of paper their relationship and maybe the angle that that pole is making with the negative real axis to define theta. Now I'm simply going to give you the relationships and then we will derive them, because I'm afraid we may run out of time. But these are what you will use. And then after you've written these down or we've sort of thought about them, then we will derive them. And then it will maybe be clear, well, where did he come up with those? How did those arise? Here is our peak time and our damped oscillating frequency relationship, the connection between omega sub d and T sub p. We will show that the time to peak is pi over omega sub d. And what's omega sub d? That's the damped frequency. That's how far that pole is away from the real axis in the vertical direction. If I wanted a smaller time to peak, what would I need from omega sub d? It needs to be bigger, so we need to be further away from the real axis. We want to shorten our peak time. We need to make our oscillatory frequency bigger. Obviously, if T sub p is pi over omega sub d, we can measure that time to peak and solve for omega sub d. Omega sub d is just pi over time to peak. And now at least we know the vertical distance our pole is from the real line. We know omega sub d if we measure time to peak. The next connection is the percent overshoot, and hopefully you remember what that was. That was that equation that was connecting your peak value and your final value of your response. You can compute the percent overshoot. That's what I'm calling PO, and the damping ratio zeta. This might look a little weird or complicated, but it's not that bad of an expression. But it is the natural log, and you can't forget taking the square root of that quantity, that ratio at the very end, to find zeta. But PO, if we had a 50% overshoot, PO would be 50. Because I'm dividing by the 100. So if I have a 50% overshoot, I'm now taking the natural log of 50 over 100, or the natural log of 1/2, and squaring it. What's pi squared, roughly? 10. So that formula is not that bad. If you remember, pi squared is roughly 10. Now we have something 10 plus what we just had in the numerator. Then we take the square root, and now we have zeta. That's our damping ratio percent overshoot connection. So you give me a peak for the output and its final value, I can find zeta. And with those, zeta and omega sub d, we can find sigma and omega sub n. And once we have that, we can get this relationship between our final value of our response and the transfer function's gain. For example, maybe we want the DC gain, or we want to find the DC gain of the system. But we may not be finding that. In this case, alpha was not the DC gain of our system. That alpha was just the numerator coefficient or constant. And A1 was the final value. So if we have the final value, somebody has to tell you how hard did you kick your system. What was A? A was the constant input. You've now calculated sigma and omega sub d from the previous two. Now we can solve for alpha. We now have alpha, we have sigma, we have omega sub d. We have that second order system transfer function identified. There may be questions on those, but hopefully now we can start to derive those and answer some of your questions. So let's now sort of go back and figure out what we have. We started with y of s. Our output was g of s, r of s. And g of s was alpha over s plus sigma squared plus omega sub d squared, and that was times r of s, which was a over s. And now we can just start walking through some of this and trying to find out how do we find the time domain expression in terms of these frequency domain parameterized versions for the output y of s. We now have a times alpha over s squared plus 2 sigma s plus plus sigma squared plus omega sub d squared. And we can also write that as a alpha over s squared plus 2 zeta omega sub n s plus omega sub n squared. And it may be to our advantage to try to compare this with a transform pair. We might actually want at some point an omega sub n squared in the numerator. And one way we can do that then is to force it to be in there by multiplying by 1. So that now I have, if I factor out the numerator a alpha and pull across the omega sub n squared in the denominator, I now have omega sub n squared over s squared plus 2 zeta omega sub n s plus omega sub n squared. And why on earth did I do that? this was my actual output response Laplace transform. But now I've written it as A is a known constant. That's how hard I kick the system. That's my input amplitude. Alpha is the gain of my transfer function, G, in the numerator. That's alpha over omega sub n squared. Those are just numbers. So A alpha over omega sub n is a constant. So I have now created a scaled version of the output, and now I have y bar that's scaled, and that will give me y of s. But what's special about y bar? Maybe you don't see anything special about y bar, but let me give you a hint. In the numerator, we have omega sub n squared. What's the constant in this second order factor? It's also omega sub n squared. So now if we looked at the final value, if we just inverse Laplace transformed y bar of s and looked at its final value, we'll see that it actually, y bar goes to 1. So we've normalized our mess, maybe, so that now if we look at just y bar, we don't have to worry about all of the different values that it could potentially go to. It's just going to eventually go to 1. Let me convince you of that, or at least show you the final value theorem. This is now y bar final value. That's the limit as t goes to infinity of y bar of t. But that's just the limit. Here's now the final value theorem. The limit as s goes to 0 of s y bar of s. That s cancels that s, and hopefully you can see what happens as we let s go to 0. S is nowhere to be found in the numerator. The numerator stays as omega sub n squared. The denominator, the first two factors in that remaining term in the denominator, those vanish because we're letting s go to 0, and what we're left with in the denominator is omega sub n squared. I've hopefully now convinced you that we've now shown that for this main dynamical piece of the output formula, which we've now formulated as a y bar, it's going to settle eventually to 1, a final value of 1. And what we want to do now is use that to actually find omega sub n or omega sub d, zeta, and alpha from the step response. And what we're going to use or realize is this omega d we are going to connect or find using the peak time. We're going to find this damping ratio zeta using the percent overshoot, and we're going to find this alpha maybe not using the y bar's final value, but the y's final value. We are going to use a final value for those. So this step response is going to be providing us with time to peak, percent overshoot, and final value. This is the hardest part of the lecture, trying to sketch these step responses. So here is, let me call this y bar of t. And this, that was supposed to be a flat version. This is now y bar final value. And we know where that goes to. Where did we say that went to in just the previous discussion? 1. And how is y bar related to y of t? If we go back and look at this connection between y and y bar, how are they related? Just by a scalar. Whatever that a alpha over omega sub n squared is, y is just a scaled version of y bar. If I assume that that a alpha over omega sub n is bigger than 1, then I can maybe draw this, and like I said, this is the hardest part of the lecture. This is supposed to be a scaled version of what I just drew. And if it is scaled properly, then they peak at exactly the same time. This time to peak is the same for both. So if we find the time to peak on y bar, that's consistent with the time to peak on y. We could now say, okay, here's y bar at the time to peak, and here is y at time to peak. And this final value in the lab, I think we've called that a sub 1. That's where we finally get to when you kick the system and it finally settles. Does it go to 1,500 counts? Does it go to 1,800 counts? What does it go to? And where did you start it? Well, you maybe applied A of 2,000. That might have been how much you tried to kick the system to make it move. Questions on the connection between y and y bar, time to peak, the maximum values, and the final values. Those should be clear from this discussion and this picture, hopefully. What we now want to do is, since y bar is normalized, it's a little easier to work with. Let's work with that to try to find some of these relationships. We will use y when we start to find the final value, or when we try to find alpha. We will use the y of t. But before that, we're just going to settle or use y bar to find zeta and time to, and omega sub d. Here's the derivation. Let's now find the t sub p, the time to peak, and the omega sub d relationship. Now, if somebody asked you to find, and they gave you a formula for y bar of t, and they said, oh, find when it peaks, what would you do with that formula for y bar of t? Maybe they hand you this formula, this expression, this function of t, and that's y bar of t, and they say, give me when this function peaks. You would take the derivative, wouldn't you? You would go back to your calculus and go, I know when we have relative maxes and relative mins, it's when the derivative is equal to 0. So we actually are anticipating finding the derivative of y bar of t. And we know how to integrate and divide in the frequency domain. Do we not? Yes, we do. That's your answer. That was supposed to be your answer. And I'm sure you picked that up on the microphone. It was just an overwhelming endorsement of that response. So we are anticipating needing the derivative of y bar of t. And that's because we know that the relative max, if that's what we're looking for, would be when the derivative of y bar was equal to 0. And we're actually going to call that t sub p. Or there's many different times, but we'll call t sub p the first time after 0 when it peaks. Well, how do we find the derivative of y bar? We don't even have that function, but we do have its transform. We have y bar of s. Y bar of s was omega sub n squared over s plus sigma squared plus omega sub d squared. Now I'm mixing sigma, omega sub d, omega sub n, but that shouldn't make you too uncomfortable. You know the connections. That's the expression for y bar. What if we were interested in its derivative of little y bar of t? How can we find that in the frequency domain? That's multiplication by s. So if we now say s and s, now this s cancels that s, and we now are looking at, on the right-hand side, omega sub n squared over s plus sigma squared plus omega sub d squared. We okay with that? That's the transform of the derivative of little y bar of t. But I don't see that in the transform table. No, you probably don't. It's probably not directly in the transform table, but we can manipulate it to make it appear. By what? Well, if the numerator was just omega sub d, we would be happy. It's not. It's omega sub n squared. But you know how to put an omega sub d in there. Multiply by 1. So now we want omega sub d only, so factor what's not omega sub d out of the numerator in the brackets and put it out front. We now have this omega sub n squared over omega sub d scaling omega sub d over s plus sigma squared plus omega sub d squared. And the reason we did that is because now we can inverse Laplace transform what's in brackets. That is in our table. That's an exponentially damped sinusoid. So that now, if we want d by dt of y bar of t, that's now the inverse Laplace transform of s, capital Y bar of s, and we have that up above. That's now omega sub n squared over omega sub d times the exponentially damped sine wave. That's what's inverse Laplace transforming that bracketed term will give us. This is now e to the minus sigma t sine omega sub dt. We okay with that? That's the derivative of y bar in the time domain. what happens to that? Or we want this to equal 0. What do we know about omega sub n squared over omega sub d? That's just a number. That's not going anywhere. That's not going to go to 0, but we can divide it out. What about e to the minus sigma t? That's always non-zero except at infinity. So the only term in that mess that has the potential of equaling 0 is the sine term. And it's obviously 0 at 0, so we want to find when is the first time after t equals 0 when this equals 0, that right-hand side. So we want this to be first time after t equals 0. And that will give us our peak time. And when will, so now we need sine omega sub dt equal to 0. That's the only piece that's going to allow that to go to 0 in a finite time window. When will that equal 0? When is the sine equal to 0? At pi, that's the first time after 0, right? At 0 it's 0, but then at pi is the first time. So now, therefore, omega sub dt equals pi. And that now gives us our peak time. T sub p, if we solve for t, is just pi over omega sub d. Was that one of our formulas we wanted to derive? Or we could now say that, well, we really wanted to use the time to peak to solve for omega sub d, and we have that. T sub p can provide omega sub d. Wow. Having a hard time with stars. Questions on that? Now, if that's the time to peak is pi over omega sub d, now what we want to do is actually, now we know what t sub p equals. If we can find an expression for y bar, we now know what t sub p is. That's pi over omega sub d. In our functional form for y bar, we just substitute pi over omega sub d for t, and we will have the peak value. We'll have y bar of t sub p. I'm talking my way through, but because I know we're out of time, and I'm not going to be able to derive all of this in the time that we have remaining. So the next step is to actually inverse Laplace transform capital Y bar and get this expression for little lowercase y bar of t. Once we have that expression, we can plug in the peak time, t sub p, and that will give us our peak value of y bar. Why do we want that? Once we have the peak value and the final value, which we know is 1, we can find the percent overshoot. And once we have the percent overshoot, we can solve that for zeta. That percent overshoot will be a function of zeta. And that's where that messy formula with pi squared in the bottom comes from. That's our connection. Then the final relationship is just to use that expression for y, the final value, and set it equal to a sub 1. We can measure a sub 1. We know everything else in the formula except for alpha, and we can solve for alpha. That's now going to be your responsibility to read these after-class notes, look at the video and notes for Lab 1, and be able to execute this on exam number 1. I'll see you on day Friday for exam number 1.